Hello and welcome. In this video, we're going to talk about sampling distributions of a sample proportion, how it relates to the central limit theorem, and all of this is going to lay the groundwork for setting up confidence intervals as well as hypothesis tests for a sample proportion. So we're going to start with a hypothetical scenario. Imagine we have data on the operating systems used by a population of 1,500 students in a large intra-data science course. In this example, we're going to ignore people who might be using a Linux distribution because they're kind of irrelevant anyways. When we first collect the data, it might look something like this, assuming we collected it in a reasonably random fashion. And this is what it might look like if we organize those observations. We might be interested in the population proportion, P, of Mac OS users. That is to say, what proportion of the students use a Mac. Intuitively, this proportion is just equal to the number of Mac OS users over the total number of students in the class. I'm going to use the dimensions of this visualization to find those values. We know that there are 30 columns, each with 30 rows fully filled with Mac OS users, and from the construct of the scenario, we know that there are 1,500 total students in the class. This evaluates to a total of 900 Mac users in our 1,500 student class, meaning that 60% of the students in the course use Macs. However, the unfortunate reality about population parameters is that we usually cannot obtain them. We're presented with a black box because we can't gather data on every individual in a population. In this example, we might know how many students we have, but it'll be difficult to obtain how many of them use Macs. We're presented with a dilemma where we cannot obtain the true population proportion. However, as you might have guessed, we can use samples to get pretty close to that value. Here's what one of those samples might look like. In this example, we randomly selected 100 students from the population, and we gathered information about their operating system. From this, we want to find a sample proportion, P hat, of Mac OS users. Just like before, we count up the total number of Mac OS users in the sample, and we divide by the sample size, little n. For this sample, 56 people had a Mac OS operating system out of the 100 students that we drew, meaning that 56% of the sample used Macs. If we plot this one observation of a sample proportion on a histogram, it's about as exciting as you'd think. That is to say, it's not exciting at all. But let's see what happens when we do more. Here we've collected 2 more samples and plotted their sample proportions. And here's 3 more. As we add more samples to our sampling distribution, I want you to make a guess as to what's going to happen. What is the shape going to be? Where is its center? And how spread apart will it be? At this point, the sampling distribution represents the following sample proportions. What are some ways that we could measure the center of this distribution? One way is the median, and that's totally valid, but in this case we're going to try using the mean, or average, of all of our sample proportions. If you need a quick refresher, that's done by adding up all of our sample proportions and dividing by the total number of samples in our distribution. In this case, our mean is 0.5952, or just about 59.5%. Let's add that line to our histogram before we move forward. The line will shift around a little bit as we add more samples, but I want you to make a prediction. Where will it end up as we collect many, many samples of size 100? Here we are at 50 samples. Here's 100, 200, 500, 2,500, 10,000, and lastly 100,000 samples. What do you notice about this distribution? To me, it's clear to see that this looks like a normal or Gaussian distribution. The parameters that I used to generate this normal distribution were that I set the mean to 0.6 and the standard deviation to 0.0490. Pause for a moment and try to figure out why I might have used these values. Let's start by talking about the mean of the sampling distribution, which in this case is 0.6. Recall at the beginning that the true population proportion of Mac OS users in our course was 60%. Every time we find a sample proportion, we expect it to vary from that value of 60% symmetrically in both directions. But if we aggregate all of the various sample proportions together, and if we find their average, we'll see that it'll lie right around the population proportion. And if we have that population proportion, we can multiply it by its complement, divide by the sample size, and take the square root of the whole thing to find the standard deviation of the sampling distribution. In other words, the square root of P times Q over N. In context, this means that the sampling distribution of p-hat is approximately normal with an average sample proportion of 60% Mac users and a standard deviation of 4.9%. What's amazing here is that the sampling distribution is agnostic to the size of the population. Given an equal population proportion p and a sample size n, the sampling distribution of p-hat looks identical whether we're talking about a college course of 1,500 students or all US adults. Any sample of size 100 taken from either of these groups will be close to a 60% success rate, but will vary from that proportion by 4.9% on average. An important and recurring theme in statistics is that there is no free lunch. And if we want our sampling distribution to look approximately normal and symmetrical and beautiful like it should be, our sample must meet a few criteria. The first criterion is that the sampled values must be randomly selected from the population. If you're running a survey, this means that you need to do a simple random sample so that every individual in the population has a fair chance of being selected. If you're doing an experiment, it means that it has to be completely randomized so that every subject has an equal opportunity of receiving each treatment, even if the drug you're testing is ineffective and sucks. The second criterion is that the sampled values must be independent from one another. In other words, the outcome of any observation should not affect the outcomes for other observations. If you're sampling without replacement, which inherently breaks this rule, it's okay as long as the sample size is no larger than 10% of the population. The third and final criterion is that the sample size, n, should be sufficiently large. A good rule of thumb is that the expected number of successes and failures should each be at least 10, or in other words, n times p should be greater than or equal to 10, as well as n times q is greater than or equal to 10. That's all I have for now on this topic. Stay tuned for some upcoming videos on using the sampling distribution to calculate probabilities, generate confidence intervals, and start testing hypotheses. On the screen now are a few practice problems that I encourage you to try out, and feel free to post your solution in the comment section below.